Okay, an electric car is travelling at a speed of 16 metres per second. Happy with that. Its mass is 1,200. Yeah, no unit change there. Calculate the kinetic energy in kilojoules. We're going to have to do a change at the end. So we know Ke equals half mv squared. We can just put those values directly into that. But at the end, we're going to have to divide it by 1,000 to get it into kilojoules, because it'll spit our answer out in joules, and then we've got to change it to kilojoules. So you can see there, 0.5 times the mass 1,200 times 16 squared, which students still forget to do, equals 153,600. So my answer is 153.6 kilojoules. Whoops. On a journey, the car transfers energy at an average rate of 17.5 kilowatts. So I'm going to have to times that by 1,000. The battery transfers a total of 126 megajoules, times that by 1,000,000. Calculate the time taken. So we can see we've got a power, we've got an energy, and we've got a time. So that's going to be our PET. And it's going to ask us to calculate the time, and it wants it in hours. So once at the end we get it into seconds, we're going to have to then divide that by 3,600 to get into hours. And that's because there's 60 minutes times 60 seconds. That's where that bit comes from. Okay, so now we can go through. So the time equals the energy divided by the power, our 126 million, because we multiplied that to get it into megajoules. 17,500, because we times that by 1,000, gives us 7,200 seconds. But now we've got the last step to change it into hours, divide by 3,600. On to the next one. Figure 20 shows an electrical device connected to the wheels of an electric car. When the car accelerates, it acts as a dynamo. So what I've got now is something spinning around, so some magnets or a coil of wire spinning around, and this is going to induce a current or a voltage. So explain how the device can be used to increase the time that the car can be driven. So ultimately we're just going to recover some energy, and therefore we're going to use less chemical energy in the car. That'll be fine. So kinetic energy, the moving car, is converted back to electrical energy, which is used to increase the chemical energy of the battery. Okay, so you've got the car with its kinetic energy. When it breaks, in a car that didn't have this energy recovery system, that would just go into heat energy, but some of that is now being recycled back into the battery, so it can go a little bit further. Why have I drawn a battery like that? Back into the battery. That's a little bit better. Only just. And there we go. So the kinetic energy of the car is converted into electrical energy, which is then used to pump electrons or pump protons back across the membrane of a battery. Okay, next one, we've got our expanded PET triangle, so E equals IVT. And it says the charging point provides an average current of 15 amps. I can leave that as it is. The potential difference is 400 volts. I can leave that. 126 megajoules, that's times 1,000,000 again. And it says can be transferred to the battery in less than 6 hours. So we're going to have to use this to get the time and then check, is it less than 6 hours? And again, we're going to have to change seconds into hours. So 126 million divided by 15 times 400 comes to 21,000 seconds. Divide by 3,600. Okay, so is it justified? Well, 5.8 hours is definitely less than 6 hours. Yes, 5.8 hours is less than 6 hours. Perfect. Calculate the total charge. So this is our vultures, whip, queens, and we know work and energy are the opposite side of the same coin, so they're equivalent to each other. Calculate the total charge. So that's Q. So I need to divide both sides by V to get Q on its own, and then we can see, so E equals, what are we after again? Sorry, Q equals E over V. And there we go. So we're going to take the energy from above here, and we're going to divide it by the charge. Q, does it give us the charge? Oh no, it's just the voltage, sorry. And it gives us the voltage 400. There we go. Stupid ray side. All I had to do was check my equation. There we go. That's that one done.